Take a look at this laboratory. Spaces like this demand surfaces that can take a beating. Testing equipment, harsh chemical spills, and constant scrubbing. You might expect the protective surfaces in these spaces to be milled from solid plastic or poured from stone, but the primary ingredient in these hyper-durable fixtures is actually ordinary paper. On its own, paper is exactly as fragile as you think it is. It tears under the slightest tension, and it completely falls apart the second it touches moisture. To take a material defined by its physical weakness and turn it into commercial-grade infrastructure, you must put it through a highly specific industrial transformation. This image shows where that process actually begins, the factory floor. These massive, heavy industrial rolls are standard kraft paper, waiting to be processed alongside rolls of printed decorative paper. The first manufacturing step is chemical impregnation. The thick kraft paper, which will eventually form the structural core of the board, is unrolled and soaked in a dark liquid called phenolic resin. The outer layers get a completely different treatment. The printed decorative paper and a transparent surface overlay are both saturated in melamine resin, which cures clear so the aesthetic designs remain visible. Once soaked, these wet, heavy sheets are fed straight through large industrial dryers to bake off the excess liquid and then chop down into specific dimensions. These dried, pre-cut sheets are then moved into a staging area known as the set room. Here, workers carefully stack them into highly specific arrangements. This diagram outlines the exact anatomy of that stack. At the base is the thick core made of multiple phenolic kraft paper sheets. On top of that sits a single sheet of decorative paper, capped off by the transparent melamine protective film. But right now, even with the chemical baths and the careful layering, this is essentially just a brittle pile of dry paper. If you exposed it to environmental threats at this stage, it would still fail. To lock those properties in, the stack is loaded into a thermopress. This machine acts as a controlled environment of crushing weight and extreme heat. Inside the press, the paper sheets are subjected to staggering physical pressure and soaring temperatures at the exact same time. Looking closer at the compressed layers, you can see the heat triggers a vital chemical reaction. The phenolic and melamine resins begin to cross-link, meaning their individual polymer chains branch out and interlock. That rapid cross-linking permanently welds the separate paper sheets into a single unified mass known as a compact laminate board. After cooling, the newly forged solid boards go through a final sizing process where their edges are trimmed down to the exact specifications required for installation in the real world. It takes the strict combination of extreme heat and mechanical pressure to force that chemical evolution, turning a stack of porous sheets into a solid slab of armor. Think back to those massive rolls of delicate kraft paper we started with. The heavy, rigid phenolic boards that roll off the finishing line bear almost no physical resemblance to them. They emerge from the factory completely waterproof, dense enough to shrug off hard impacts, and feature a clean, aesthetically pleasing finish. This entire process demonstrates the principles of material engineering. By combining a highly vulnerable organic base with advanced resin chemistry and extreme physical force, manufacturers create a product that behaves nothing like its starting ingredients. It proves that with the right application of chemistry and pressure, we can completely bypass a natural material's inherent physical limits. So the next time you lean against a heavy-duty lab table or open a commercial locker, remember that its engineered strength is secretly built from ordinary paper.